Hello everyone, this is lecture 14 of the subject analog circuits. In this class, I am going to discuss the remaining properties of negative feedback which are left, and then basic feedback topologies. So, in the last class in lecture 13, I was discussing the basic properties of the negative feedback. So, there I had discussed 3 properties with derivation in lecture 13. Now, the remaining 2 properties I am going to discuss in this class. So, before this class I had discussed 3 properties, and those 3 properties are gain desensitivity, bandwidth extension, and one more property, that is your interference reduction. Now, the 4th property is reduction in nonlinear distortion. So, for any amplifier it is desirable that the distortion should be less, fine, because if there is a distortion at the output of the amplifier, then it means that the shape of the signal is changing. So, in amplification we should be careful that the shape of the signal should not change. If we are applying the sine wave at the input, then obviously the output it should be sine wave with the amplification, but the shape should not change. If the shape is changing, that means there is distortion, and due to that distortion the information may lost. Okay. So, by using negative feedback, this distortion can be minimized. So, to understand it, let us consider that if the open loop gain is 1000 for any amplifier, and if this open loop amplifier it is reduced from 1000 to 100. For example, if the open loop gain is reduced from 1000 to 100, then we have to calculate the effect on the closed loop gain. So, we can calculate it corresponding to 1000 open loop gain, your closed loop gain AF1 it is 90.9 if your beta is 0.01. This is just for an example, fine. Beta is your feedback ratio. Corresponding to open loop gain is equal to 100, A is equal to 100 and beta is equal to 0.01, your closed loop gain is 50. Now, you can see that when your open loop gain is reduced from 1000 to 100, that means by the factor of 10, then your closed loop gain it is reduced from 90.9 to 50. Now, you can see that the percentage change in the closed loop gain it is very less, it is less than 2, but in case of open loop gain it is more. So, the point is that if due to the change in temperature, due to the change in circuit parameters, your open loop gain is changed from by a larger factor, then your closed loop gain it is not changing by that particular factor. That is a good thing, because in any amplifier we want stable gain. The gain should not change if there is a variation in temperature, if there is a variation in circuit component values, that is desirable. So, if your closed loop gain is not changing by that particular factor, it is a good thing, it means that it is improving the linearity. If it is improving the linearity, it means that it is reducing your nonlinear distortion. So, there are 2 graphs. Graph A is the transfer characteristics, that is the input voltage versus output voltage. Graph A is for amplifier without feedback, graph B is for amplifier with feedback. Now, you can see that in the case B, in the graph B, using negative feedback we are getting more linearity. So, by the help of negative feedback we can reduce the nonlinear distortion, we can improve the linearity of the amplifier. This linearity is very important, this linearity is very important, because we want linear amplifier, we design linear amplifier and we want that this linear range should be high, If the linear range is high, it means that for a wider range we can amplify the signal without distortion. Next property of negative feedback is it can control the input and output resistance. Now, we can increase the input resistance and output resistance, we can decrease the input and output resistance. So, there are 4 cases. So, input resistance will increase or decrease, output resistance will increase or decrease, it totally depends upon the selection of appropriate feedback topologies. Now, what is this feedback topology? We need to understand it. There are 4 kinds of feedback topologies, or we can say that there are 4 kinds of amplifiers. First one is voltage amplifier, second one is current amplifier, third one is transconductance amplifier, fourth one is transresistance amplifier. And these amplifiers are classified based on the quantity which is to be amplified based on the quantity which we are getting from the amplifier. For example, this is your amplifier. If we are applying voltage and we are getting voltage, this is called voltage amplifier. Input is voltage, output is voltage. If your input is current, output is current, that is your current amplifier. If input is voltage, output is current, then that is your transconductance amplifier. In transresistance amplifier, input is current and output is voltage. We can understand it very easily. Transconductance means output current upon input voltage. It means that at output there is a current, at input there is a voltage. At output there is a current, at input there is a voltage. Transresistance means, that is also called transimpedance amplifier. Resistance means output voltage upon input current. So, at the output there is a voltage and at the input there is a current in transresistance amplifier. So, these are the 4 amplifiers, these are the 4 feedback topologies which we are going to understand, and we will see that we can change the input and output resistance by selecting a proper amplifier, and what should be the input and output resistance for a particular amplifier, that we are going to see in this particular class. So, the point is that before I discuss anything, let us see the case of voltage amplifier. Voltage amplifier. See, in voltage amplifier, your input is voltage, output is voltage, and in feedback structure, what we do in feedback, for example, we are considering this voltage amplifier. This is your voltage amplifier, your input is voltage, output is voltage. Now, this is your open loop amplifier, amplifier without feedback. Now, we are connecting a feedback network here whose feedback factor is beta. Now, the output of this feedback network, it is subtracted from the input because of negative feedback structure. Now, see what is happening in this particular voltage amplifier with feedback. We are taking the sample of the output and we are mixing that sample with the input. So, 2 important terms here. We are taking the sample of the output. It means that at output we are doing sampling. We are taking the sample of output. So, sampling occurs at output. Now, we are mixing this sample with the input signal. It means that at input mixing occurs. So, the terminology should be clear. At the output sampling happens, at the input mixing happens. So, this voltage amplifier, it is also called voltage mixing, voltage sampling, voltage mixing, voltage sampling. Similarly, if it is current amplifier, then at the input there is a current, at the output there is a current. So, it will be current mixing, current sampling. So, you have to just understand one thing, at the input, at the output, it may be voltage, it may be current, but the term is same. At the output there is sampling, at the input there is a mixing. Why? Because from the output we are taking the sample of the output and we are just mixing at the input, fine. So, this voltage amplifier, it is also called voltage mixing, voltage sampling. Another term is there for voltage amplifier, that is based on the connection, whether it is series connection or shunt connection, parallel connection. Now, see that in this voltage amplifier, that is with feedback, what should be the type of the connection, series or shunt at the input, series or shunt at the output. How we decide it? We can understand it, just focus on it. At the output there is a voltage. Now, we need to take a sample of that voltage. How we can take the sample of the voltage? For example, if there is a resistor and if we want to measure the voltage across that resistor, how we measure it? With the help of voltmeter. We connect that voltmeter in parallel to measure that. So, it means that if we want to take the sample of the output, it means that at the output there should be shunt connection. Now, at the input two voltages are mixed up, at the input two voltages are mixed up. So, two voltages are added or subtracted. How it happens? Two voltages are mixed up when they are in series, because in parallel the voltages are same. So, at the input side the connection will be series. So, this voltage amplifier, it is also called series shunt feedback amplifier. Series shunt feedback amplifier. So, the point is that voltage amplifier, it is also called voltage mixing, voltage sampling, it is also called series shunt feedback amplifier. Fine. And what is desirable for voltage amplifier in terms of resistance? What should be the input resistance? What should be the output resistance? For any voltage amplifier, in order to avoid the signal loss, the input resistance should be high and the output resistance should be low. We had designed these amplifiers, these voltage amplifiers in unit 1, your common emitter amplifier, we have analyzed them in fact, and your common source amplifier in MOSFET. Fine. So, the point is why the input resistance should be high and output resistance should be low, that can be understood with the help of the basic structure of the amplifier also. From here also we can see that since there is a series connection at input, so the input resistance, it is increased by a particular amount. Since there is a shunt connection at the output, so the output resistance is reduced by a particular amount. Now, see to it. In unit 1, the amplifiers which you have studied, that is without feedback, there is no feedback. Now, by using negative feedback, the input resistance of voltage amplifier, it will be increased and the output resistance will be reduced. That is desirable, because for any voltage amplifier your input resistance should be low and output resistance should be high. This is desirable for any voltage amplifier, and by using negative feedback just we are enhancing this parameter. Your input, sorry, input this is wrong in fact, just I want to correct it. For any voltage amplifier the input resistance should be high and output resistance should be low. This is desirable for any voltage amplifier. Input resistance should be high and output resistance should be low, and by using negative feedback we can increase the input resistance further and we can reduce the output resistance further. That is the advantage of negative feedback. Fine. So, in voltage amplifier it is intended to amplify an input voltage and provide an output voltage. Input is voltage, output is voltage. So, it is basically your voltage controlled voltage source, and of course, for any voltage amplifier the input resistance should be high, output resistance should be low, and the term which I have discussed, that is voltage mixing, voltage sampling. It is also called voltage mixing, voltage sampling, it is also called series shunt feedback amplifier, that is another term for voltage amplifier. This is the basic block diagram of feedback voltage amplifier. You can see that this is your basic voltage amplifier, and if we are connecting a feedback network, obviously negative feedback, then you can see that at the output side there is a shunt connection and at the input side there is a series connection, and at the output there is a voltage, at the input there is a voltage. You can see that your feedback is voltage Vf and your input is voltage. Now, this Vf is mixed up with Vs. So, that is why it is called voltage mixing, voltage sampling. Next is current amplifier. In current amplifier the input is current and output is current. that is why it is called current amplifier. Now, what is the another name of this current amplifier? Since at the output we are taking the sample of the output and we are mixing that sample into the input. So, it is called at the output side, since sampling is occurring. So, it is called current sampling. At the input side mixing is occurring. So, it is called current mixing. So, current amplifier, it is also called current mixing, current sampling, and in terms of series shunt connection we can understand it, since input is current and output is current. So, just think about it, if at the output there is a current and we need to take a sample of that current, how we can take it, in series or shunt? In series the current is same. So, at the output there will be series connection, because at the output there is a current and we need to take that sample of current, and at the input two currents are mixing up, two currents will be mixed up in series or shunt, in shunt, because in series the current is same. So, at the input the connection is shunt, that is why current amplifier it is also called shunt series feedback amplifier. It is also called current mixing, current sampling, and for any current amplifier what is desirable in terms of input and output resistance? Your input resistance should be low and output resistance should be high, that is desirable for a current amplifier. And by using negative feedback in current amplifier, what is happening? The input resistance will further reduced and output resistance will further increased. So, it means that whatever input and output resistance is desirable from any amplifier, that is fine. Now, further by using negative feedback we can further enhance the input and output resistance, desirable input and output resistance. That is the advantage of negative feedback, use of negative feedback in amplifiers. Now, these things I have already discussed. This current amplifier, it is also called current mixing, current sampling. This feedback topology is called shunt series feedback. Next one is transconductance amplifier. In transconductance amplifier, conductance means current upon voltage, and the gain will be output current upon input voltage. It means that at the output there is a current, at the input there is a voltage. Now, since at the output there is a current, so we say that now we will take the sample of current. So, it is called current sampling, and at the input since there is a voltage, so two voltages are mixed up. So, there is a mixing phenomena at the input. So, it is called voltage mixing, it is called voltage mixing. So, it is fixed, mixing will be at input, sampling will be at output. So, transconductance amplifier it is also called voltage mixing, current sampling. Now, you can see that in terms of connection how we decide it, series feedback, it is called series. Why? Because at the output there is a current and we need to take the sample of current. How we can take it? The sample of current can be taken only in series, because in series the current is same. So, at the output there is a series connection, at the input since the voltage is to be mixed, two voltages will be mixed up if they are in series, because in parallel the voltage is same. So, at the input there will be series connection, that is why transconductance amplifier it is also called series feedback amplifier. And of course, for transconductance amplifier it is desirable that your input resistance should be high, your output resistance should be high, and your negative feedback it helps in achieving higher input resistance and higher output resistance. We will derive these expression of input and output resistance for all amplifiers with the help of negative feedback. Next is trans resistance amplifier. Last is trans resistance. Resistance means voltage upon current, and the gain of the trans resistance amplifier will be output voltage upon input current. So, at the output there is a voltage, at the input there is a current. So, another term for trans resistance amplifier is your voltage sampling, current mixing. At the output there is a sampling, at the input there is a mixing. So, trans resistance amplifier is also called current mixing, voltage sampling. And in terms of connection, you can think about it. since at the output there is a voltage, we need to take the sample of voltage. How we can take it? In shunt, fine. So, at the output there is a shunt connection and at the input there is a current. So, two current will be mixed up only in shunt, only in parallel. So, there will be shunt connection at the input. That is why this trans resistance amplifier, it is also called shunt feedback amplifier. And of course, for any trans resistance amplifier, your input resistance should be low, your output resistance should be low. Sometimes this trans resistance amplifier is also called trans impedance amplifier, and by using negative feedback we can further reduce the input and output resistance that is desirable. So, the summary is there are 4 amplifiers: voltage, current, transconductance and trans resistance. In voltage amplifier, the input is voltage, output is voltage. In current amplifier, input is current, output is current. In transconductance, your output is current and input is voltage. In trans resistance, output is voltage, input is current, fine. And this voltage amplifier, it is also called series feedback amplifier. Current amplifier is also called shunt series feedback amplifier. Transconductance amplifier is also called series feedback amplifier. Trans resistance amplifier, sorry, trans resistance, yes, trans resistance. Trans resistance is also called shunt feedback amplifier. Now see, although we will derive the expression of input and output resistance for these amplifiers in the next class, now before that class just see to it. With the help of negative feedback, if your resistance is increased, then that increased resistance will be by the factor of 1 plus A beta, and if the resistance is decreased, then that will decrease by the factor of 1 plus A beta. That 1 plus A beta is called amount of feedback. 1 plus A beta is amount of feedback. A is your gain without feedback, beta is your feedback ratio, A beta is the loop gain, 1 plus A beta is the amount of feedback. So, the point is that in voltage amplifier, the input resistance with feedback, it will be equal to Ri into 1 plus A beta, and your output resistance will be reduced by the factor 1 plus A beta. So, the point is that in case of voltage amplifier, when we apply negative feedback, in voltage amplifier, then the input resistance with feedback, it will be equal to Ri into 1 plus A beta. Ri is the input resistance without feedback. Now, you can see that with the help of negative feedback, your input resistance is increased by the factor 1 plus A beta. Similarly, the output resistance with feedback for voltage amplifier, it will be R naught upon 1 plus A beta, where R naught is the output resistance of voltage amplifier without feedback, ROF is output resistance with feedback. Now, your output resistance with feedback, it will be reduced by the factor 1 plus A beta. So, with the help of negative feedback, we can further enhance the input resistance, we can further reduce the output resistance with the help of negative feedback. So, although we will derive these expressions in the next class, but you can write the expression of input and output resistance for all the amplifiers. For current amplifier, what is desirable? For current amplifier, the input resistance should be low and output resistance should be high. So, when we apply negative feedback, in current amplifier, then what happens? Since the input resistance should be low and output resistance should be high, because there is a shunt series connection, then your input resistance with feedback, it will be Ri upon 1 plus A beta, and your output resistance with feedback, it will be R naught into 1 plus A beta. Now, just see to it, without feedback your input resistance is Ri and your output resistance is R naught, but by using negative feedback in current amplifier, what is happening? Your input resistance is further reduced by the factor 1 plus A beta and your output resistance is further increased by the factor 1 plus A beta. And for any current amplifier, it is desirable, in order to avoid the signal loss, it is desirable that the input resistance should be minimum, output resistance should be maximum. and in ideal case, of course, in ideal case the input resistance should be 0 and output resistance should be infinite, and we want to go towards this ideal case, although we cannot achieve practically, but we want that. We want that the input resistance should be low and output resistance should be high, and with the help of negative feedback we are getting better results. That is the advantage of negative feedback. So, with the help of negative feedback we can change the input and output resistance by the factor 1 plus A beta for different amplifiers, for these particular 4 amplifiers which I have discussed. So, we will do the derivation part, that how this negative feedback, it is changing the input and output resistance by a certain factor, that factor is 1 plus A beta. That is the derivation part that I will discuss in the next class. This is the reference. Thank you.